one that I gave maybe 6 months ago. Really, you can't hear that? Okay, so this talk is basically an incremental update of one that I gave maybe 6 months ago, where we put forward an idea for a new driver infrastructure for graphics, 3D graphics under Linux. Basically addressing a bunch of developments that have occurred in hardware and in the software environment and the things that we wanted to do with 3D on Linux. Basically, I've included the first few slides here, and we'll start with that. Basically, it helps to start with a look at where things were previously, or perhaps still are, in production in the mainline, what you're actually using in terms of open source 3D graphics drivers. Basically, we've got a thing called Mesa, and it's probably bigger than that block, but I think that's disproportionate to emphasize the fact that actually it's not that much bigger. The DRI drivers over the years have gotten larger and larger as they've had to deal with more and more aspects of the peculiarities of OpenGL, the peculiarities of our interaction with the X server, with the kernel module, and so forth. And all of these competing influences are sort of boiling away in here, fighting with each other, and working to just make it hard to do interesting things with the drivers, making it hard to add features, making it hard to fix bugs, making it hard to get things stable, or ever really done. I guess over the years we've written a few drivers, and we've noticed that there are probably some possibilities to cut this thing up and to break it into manageable chunks. And so that's basically the starting point for where we've gone. Basically, we've looked at putting interfaces into the middle of the driver, taking a chunk off that's really all about GL, taking a chunk off that's all about the X server, kernel module, that sort of stuff, and leaving this chunk in the middle, which is the bit that interests me personally, which does the hardware interaction. It really is the driver. So that's what we ended up with. This is what we set out to pursue, and this talk will be a bit of a status of where we're at with it. We've introduced a couple of new things here. First, this state tracker concept. Basically, that state tracker looks a lot like an old-fashioned Mesa driver, but rather than targeting a particular piece of hardware, it's targeting this interface here, which is really the interface to Gallium 3D. So that's the glue that takes you from Mesa to sort of old world of Mesa to a sort of a newer, cleaner set of interfaces. Well, let's get through. The second interface is this guy here, which we're calling at this point the WinSys interface. It's the back-end interface that abstracts away things like clip breaks, command submission, any sort of hardware interaction, any aspect of talking to the kernel module. All those things are sort of behind that interface. And this interface really looks a lot like a batch buffer submission interface, and perhaps a memory manager interface. So it's memory management on the card and command submission, and that's kind of it. And the rest of the task of turning that into a working driver for the particular environment that you care about, be that DRI or something else, is all pushed into this module back here, the WinSys. And that diagram is still pretty much correct. There's been evolution, but we've been pursuing this for a little while now, and it's looking like it's a good design. So since then, those interfaces have evolved. We made a first stab at things, and there have been people out there who've been tracking this work. feel their pain because it's been hard enough for us to keep up with it, and you know, if you were doing this as a sort of spare time thing, I think just whoa. If you're doing this as a spare time thing, you'd probably find that you spend most of your time just dealing with the interface changes that have occurred over the last few months. That's it's kind of hard to avoid that because it's hard to jump right in with the right interface from the start. We've evolved as issues have come up. It's inevitable. But hopefully now we're moving to a point where things are stabilizing. We've got a pretty good idea of what we're doing with these interfaces. There's some things on the horizon, but I'm hoping that these guys' pain will be drawing to an end, and that that we're getting there basically. So that's all kind of boring. Okay, so the thing that you'll miss from this slide is this is my view of the driver. It's all about drawing. So some other people care about allocating surfaces and doing swap buffers and things like that, all the stuff that GLX handles. And GLX is just kind of off the horizon here. So we've had to, probably the big change to this diagram is that there's a line going down through here that handles those things. And this really looks like a 3D rendering context. So the bit that's missing really corresponds to a per screen driver. So this plan is very good for drawing context. It pretty much ignores how you create a context and what environment those contexts live in, and that's important for a couple of reasons. I think the key that tripped this up is the fact that there is sharing of surfaces and various other data structures between contexts, and to really achieve that properly, you do need some sort of external persistent entity that manages that. So that was kind of missing from my worldview, and that was kind of deliberate just to get to the core of what we really wanted to achieve. But since then, reality has asserted itself, and we've had to deal with that a little bit. Okay, in terms of development, we've got some hardware drivers running. They're all in various states of completeness. Basically, the 915 has been our workhorse. It's a simple piece of hardware. It's well behaved. We love it, and it's been kind of the mule that we've built this thing on the back of. SoftPipe is the software rasterizer, and so in terms of status, these are pretty much in order of doneness, I guess. So 915 is, it runs most stuff. It could use some work. It's there, it exists. The biggest problem with it is that it's probably impossible for anybody in this room to build. Basically, at the time we started this work, we all had test machines that had 915 running on a fine. We just kept them in that state. Now nobody knows how to recreate them. They've all got various odd kernel modules, X drivers, patches, and things like that just happen to work at that point. There's no way that I could give you a recipe to build that driver, and that's something that we're going to fix pretty shortly. Interesting stuff has happened on the head, on the trunk since the time that we started that work. So DRI2 has landed. What else? There's been evolution in the memory manager, etc. And it's going to be very interesting for us to get this driver into that environment and bring it up to speed and see what the world looks like with that there. So SoftPipe is what's called the software rasterizer. That's probably really it's the most complete of the drivers. I guess it's number 2 because it's not as interesting as a hardware driver to most people. It needs some performance work. It'd be a very interesting project if anybody wanted to take it on. Basically, if you've got an interest in runtime code generation or doing cool stuff that people will love you for, SoftPipe has opportunities. Then, further down we spent a bit of time on the cell driver, I'll talk about it later, and there's a fairly functional 965 driver out there that, again, it's, if you didn't like the 915 driver, the fact that you can't build it, you won't like the 965, because, it's even worse. And then there's, it's impressive that throughout this turmoil and this rapid development process that some people out there have even tried to track it. In fact, there's at least two groups who've done that. And here on the front row, there's been an effort in Nouveau, I believe, to get a G40 driver on the gallium stack. MD40. And Jerome has put some effort into R300 as well. Software rasterizer I talked about. You get some buzzwords like LLVM, which is a really cool compiler architecture for useful for runtime code generation. We have code there to compile fragment shaders dynamically using LLVM. To really finish the project, you want to compile a lot more than just the fragment shader. You want to integrate that dynamic compilation process with something that looked at drawing a whole triangle or a bunch of triangles and code generate the whole lot. If you took that on, you'd probably be rewarded with a very capable software rasterizer. That's the task for somebody. I don't think it's not really on the horizon to do that, as cool as it is. 915 doesn't track DexOrg, as you know. We're going to fix that. We're going to make it fast. You'll love it. Yes, and this is the other thing. So part of this process, if you go back to this diagram, here we are. This is if you think about dependencies, this piece here, which is really the driver now, that really the only thing that it really knows about or has any knowledge of is how to drive the hardware. It really doesn't know anything about OpenGL. It doesn't know anything about the DRI. It doesn't know anything about windowing systems generally. The nice thing about that is, well, two nice things. One, it makes it very straightforward to write one of these. You don't have to think about that stuff while you're working on this code. But as a side benefit, it means that code can run in a whole lot of different places. You can't realize swapping out these other components. So the thing that we have done, and this is TG's a business, we like to pay our wages. This thing, we've got it running on Windows, and it works. This thing actually exists in some sense as a DX9 driver. What can I say? You don't care, but it's helpful for us. So the point is, if it does that, then it'll do whatever you like, whatever you care about, whatever obscure set of API and operating system and windowing system that you've got an interest in. You have the possibility to port these drivers to that environment, in a manageable way. It's feasible. And this is something that really wasn't possible with, vaguely possible with the DRI, but it's a lot of work. You probably would have ended up with unsupported fork of the DRI drivers. This is a new thing. So the point is that if you care about portability, this is a win for you. And you don't even need hardware. This is probably not that applicable to everybody here. But if you're trying to run a driver, the driver now no longer actually talks to hardware. It talks through a very stereotyped interface that you can put whatever you like behind. So if you want to analyze the hardware interactions by dumping files, if you've got a simulator that runs in a batch sort of a way, if you just don't have the hardware but want to test the driver for some change, whatever, that's possible, and this works as well. Probably the most interesting thing to do with this is capture and replay of the replay. so if you're capturing files, then you probably also want to be able to replay them. So that would be a useful thing to tack on at some point. I'm ripping through it. Okay. Okay, so probably the sexiest thing that's going on in Mesa with this architecture right now is the cell driver. What have we done? Again, this code is out there, it exists. You can pull it down. If you've got a PS3, you can install Linux on it. I'm sure you know that. This is a project to actually bring 3D graphics to your PS3. It's possible. So, in fact, Brian Paul has primarily been working on this. He's really plugging away at it for a little while now. He got the first triangle in December. And by that first triangle, rasterization is being done on the SPUs. Vertex processing currently being done on the PPUs. So we're really treating the system a bit like a regular computer with a CPU here and this sort of very odd graphics card, sort of rasterization level graphics card here. That's a useful way to start bringing it up. I think the plan ultimately is to really do everything on the SPUs, so vertex processing, clipping, etc. But the initial task is rasterization. So that's now running simple Mesa demos. Basic texturing is working. The main missing parts are runtime compilation of the fragment shaders. So interestingly, I probably didn't get a lot of characteristics of this interface here. The abstraction that it makes of the hardware is to throw, one of the characteristics of the abstraction it makes is to throw away the fixed function view of the world, so lights and matrices and texture environment, all the sort of classic GL stuff is being thrown away. Basically, the hardware looks like there's some state, there's a vertex program, and a fragment program, and there we have a pretty expressive language for describing those programs, and between them it's possible to implement all of the classic OpenGL transformation, lighting, clipping, texturing, etc. Through these fragment and vertex programs. This is a very clean way of describing graphics state. It means that instead of dealing with arcane concepts like lights and how do you optimize a light and how do you code generate a light, which is an odd, it just doesn't make sense. You're dealing with sort of sensible things like how do I code generate a program at runtime? I have a program I want to compile it, I do it at runtime. That's easy for people to understand. It means you don't have to be a graphics expert to work on the performance parts of a driver. You have to be a compiler expert. Is that better? Yeah. So what's missing currently is that dynamic compilation step. So we've got a couple of hard-coded shaders that we select between. It's enough to get simple lighting and shading and basic texturing working. It'll get done, but if anybody's interested, it would be a fun project as well. If you've got an interest in any of this stuff. So that's what the first triangle looked like back in December. I thought we'd better have a triangle. It's indicative. This is how if you do a lot of graphics, this is your life. Basically, by the time you get to this, you're getting there. The nice thing about this is Brian colored each of the squares slightly according to the SPU that's doing the work. And you can see they join up very nicely. And that's pretty much still how it's working. So it packages up bits of rasterization work, farms them out to the SPUs, gets the results back. That's the job done. And probably going forward, there are a lot of ways to optimize that. There's probably 2 or 3 different strategies. I guess the thing about the cell chip is that it has no hardware architecture. You're not forced into implementing any particular graphics pipeline on that chip. So you have a possibility to choose your pipeline. So most of these drivers, the software drivers, emulate or modeled after some set of behaviors that's been prototyped in hardware or developed in hardware. Because those guys have thought about it a lot more recently than anybody doing software rasterization. And so in terms of the cell driver, you've got a choice as to whether you model a deferred mode renderer, like I can't think of a good one, probably the 915 in zone rendering mode, if that means anything. Or whether you model something that's a bit more dynamic in the way that packages work up, like a modern NVIDIA or ATI GPU. There's no constraints on you because the hardware is a completely general purpose computation device. It's just a very, very strong one. That really, I mean, if you think about it, the latest IBM revision of this chip is pushing, I believe, 6 gigahertz. It's got, if you compare, so GPUs have got a lot of cores, but they don't really push a very high clock rate. They max out about gigahertz, something like that. So I think there's a possibility that a well-optimized cell driver could be a pretty competent mid-range GPU, especially if you think about the fact that the cell's been out for a few years now. If you're going to compare it against GPU hardware, you probably compare it against the hardware that was being released at the same time that the cell came out. I think in that cohort of GPUs, you probably find that a well-optimized cell driver is actually a contender. But we have to get there first, and that's happening. Okay, so I guess if I transition to some of the things we've learned along the way, I guess if we go back to the DRI, the original driver, I gave a pretty rosy view of that. I showed you a simplified picture of it. What was missing is this large other chunk of code sitting out there that basically implements a second set of drawing paths which are used on fallback. So a fallback is obviously some set of GL state that we don't really know how to program the hardware to do. And basically the strategy that we've used for dealing with that is to say, well, we can't do it, let's get the software rasterizer to draw it. And that's pretty unsatisfactory. You get a correct image, you satisfy the conformance test, but people assume the driver isn't working because it takes seconds or minutes to render a frame, and that's not what people are really looking for in their drivers. In fact, if given the option, most people will turn fallbacks off and accept minor rendering errors, but to have a usable application. So that's jumping ahead a bit. So in terms of gallium, we did have, and this impacts on Jerome's talk a little bit. We had a strategy for fallbacks that basically was sketched out and never fully implemented, and that's basically along the same lines. It sounds like I'm saying this will never happen. It could still, but I guess I'd like to think there was a better way than just coming up with another fallback path that used the same trick of the software rasterizer. So fallbacks are bad. We don't like them. Can we do better? Well, I think we probably can. We've got hardware that's Turing complete. Ish. Well, yeah. Right. We've got smart hardware, we've got hardware that's flexible, we've got a nice layered interface. You know, we can probably come up with ways of getting the rasterization that we need, even though it doesn't obviously map onto hardware. So things that were typically fallbacks in the past are anti-alias points. In GL, there's interesting rules for how these are supposed to be drawn that don't map well, or don't map natively onto the facilities that are provided in regular GPUs. GPUs are really optimized to draw triangles, to apply a shader to those triangles, to stick the result out to memory. It's pretty hard to map the round AA points onto triangles natively without playing with state, and that's what we do. We play with state behind the scenes. So if you can imagine somebody drawing an anti-alias point, applying to that a particular shader, or a particular set of states, basically what we end up doing is writing a second shader that effectively gives you the texture. We'll end up drawing a quad with a second shader that discards all of the pixels that shouldn't be in the round point, and applies the anti-alias sort of fall-off coverage stuff to that shape, and composing that shader with the shader that the application has actually provided. So we'll glue these two shaders together in the state tracker, basically outside of the driver. There's a piece of code that's written once and works on any piece of hardware that basically constructs a new GL state out of the desired application state and what we need to do to implement AA points. And then just sends it down to the hardware driver. The driver never knew it happened. The driver just finds it's being asked to draw a quad with a particular shader. It loves it, eats it up, and you get an AA point. There's no fallback. Generally, that's a better approach than what we're trying to do more of. And the goal with the 915, and the 950 is a bit of a classic because it does have some of these warts, and it does have fallbacks in the current driver. And our goal in the sort of medium term is to basically demonstrate this concept by putting together a 915 driver that has no fallback. We'll render anything in GL 1 point whatever without resorting to a software rasterization. Okay, and this is the thing that I mentioned earlier. The lovely diagram omits any sort of information about how GLX is supposed to be implemented. This was obvious from the start because swap buffer is a GLX concept, and we ended up with this sort of weird, layer breaking jump into there, and it really, the layers don't break. It's just that the things, the components that implement that jump were missing or absent from the diagram. And similarly, other things like creative surfaces, etc., really need a little bit more to be correct. Blah blah blah. So we've ended up. So that WinSys thing. This has basically been the subject. Probably most of the evolution is happening here, and that's a little bit surprising because of all these boxes. This is actually a very small piece of code. This is 3,000 lines of code, I think, in the current repository. But what you'll see if you look at it is it's just a box of interfaces. There's 5 or 6. So there's coming into here. There's actually 2 interfaces here. So one to the DRI, regular DRI driver interface, 3. Then it's talking to the DRM, 4, and to the DDX, the X server. So there's 5 interfaces jammed into 3,000 lines of code. And basically, yeah, for this to be correct, it's had to split a little bit. So it's, there's a line through there. Above the line, we have per context stuff. So basically the things that the command processing, drawing, etc. stuff. Below the line, persistence per screen object that handles service management, etc. Context creation, that sort of stuff. Okay, so that's to illustrate how much is in there and how surprisingly complex it is. That's it, kind of broken out into its components. And I think this is probably closer to the truth as to how this is going to be implemented going forward. I think we'll probably see these three parts of the WinSys get split off into their own little modules. It's not as nice, but it works. And the nice thing about that is, so with that previous, with this everything in one place situation, you end up with the same problem we had with Mesa drivers as a whole, that you to create new ones of these for new